Hi, welcome to Chapter 15, Chemical Equilibrium. Overview Part 1, where we're going to talk about the concept of equilibrium, the equilibrium constant, and understanding and working with equilibrium constants. So what is the concept of equilibrium? So here we have a picture of frozen N2O4, and it's in a sealed container. And as time progresses and it warms up, some of the N2O4 will become NO2 gas. And NO2 gas has a brown color to it. And then as it warms up some more, you're going to end up with some more NO2 gas. And you're going to actually reach a point where you're not going to form any more NO2 gas, because as you're forming NO2 gas, the reverse reaction is going to start to kick in, and you're going to form N2O4 gas. So even if you leave this overnight and come back, it'll be the same color. That's because we are at equilibrium. And what is equilibrium? Chemical equilibrium occurs when a reaction and its reverse reaction proceed at the same rate. So it goes forward and backwards at the same rate. So in the figure above, equilibrium is finally reached in this picture here. So let's examine the concept of equilibrium a little bit more. So here's our reaction that was diagrammed in the previous slide. And you notice that we have these arrows pointing in both directions here. That means you're at equilibrium. That means that the forward reaction and the reverse reaction can occur. So let's look at this diagram here first. So we're starting with 0 NO2, which is the reactant. That kind of makes sense. And we're starting with a high concentration of N2O4. And what happens with time? The amount of N2O4 starts to decrease because we are making NO2. So that starts to increase. And then we're going to reach a point where their concentrations do not change anymore because we are at equilibrium. Equilibrium is achieved here. You notice the concentrations have stopped changing. So if we plot the rate, okay, and remember your rate law is K for the forward reaction is K times the concentration of N2O4. We'll put F for forward. And the rate for the reverse is K reverse times NO2 squared. So initially, the rate is decreasing until we reach a steady rate. And this rate of making NO2 is increasing until we reach a steady rate. At equilibrium, the rates are equal. Notice they're equal. So as the system approaches equilibrium, both the forward and the reverse reactions are occurring. So both are happening. At equilibrium, your forward and reverse reaction will proceed at the same rate. Once you achieve equilibrium, the amount of each reactant and product will remain constant. See, it's remaining constant here, constant. In a system at equilibrium, both the forward and reverse reactions are being carried out. As a result, when we write the chemical equation, we use a double arrow. Equilibrium. Because the forward and the reverse reaction are both occurring. So what does it really mean when you have a system in dynamic equilibrium? Products are being made, but reactants are being made at the same time. The total amount of reactants and products don't change. Neither reactant nor product can escape the system, so it's in a sealed system. It cannot escape. There is a ratio of concentration term that is constant. Okay, so this is like what it means in chemical terms. Let's talk about it in like real life. You are running on a treadmill. Okay? The system is in systems in equilibrium are balanced. So if you are running on a treadmill and you are in constant motion, you're constantly running, however, you are not moving forward or backwards. As fast as you run forward, the treadmill is moving backwards. You are in equilibrium with the treadmill. So that's what's going on with your chemical reaction. The forward reaction is occurring, but so is the reverse reaction. So it appears like you're not moving, just like you running on the treadmill. You are actually running, but you are not moving forward or backwards. You're in equilibrium. So when we're in equilibrium, we can compare our rate laws. First, we have to assume both the forward and the reverse reactions are elementary reactions, okay, and the temperature is constant. So for the forward reaction, we have this as our rate law, Kf meaning forward. For the reverse reaction, we have this as our rate law. Remember, because they are elementary reactions, we use the coefficients here as exponents. If you are at equilibrium, the rate of the forward must equal the rate of the reverse. So you could set your two rate laws equal to each other. And then you can put like terms on each side. So you can take the ratio of the rate constants, which are the little k's. Again, it's at constant temperature. And now you'll have an expression for the equilibrium constant. Equilibrium constant is a capital K, EQ meaning equilibrium. It's equal to K of the forward over K of the reverse. Or it's equal to the concentration of the products over the reactants raised to whatever power is the coefficient in the balanced equation. So the Haber process is a famous chemical process that actually is very important even in today because it helps us produce NH3, which is used in fertilizer, which helps us grow plants. But anyway, considering the Haber process, which is how the industry produces ammonia, we have this equilibrium reaction right here. So the equilibrium constant for this would be your products raised to the coefficient divided by your reactants raised to each coefficient. So you have your products over reactants. And this is called your equilibrium constant. Now the C here is because we are dealing with concentration. So what do you start with to reach equilibrium? Okay. So does it matter what you start with to reach equilibrium? Well, let's see. So in this case, we are starting with only reactants. So here are our reactants, H2, we're starting with this much, and N2, we're starting with this much. And the reaction starts to proceed. The concentration of our reactant starts to decrease as we're making our products. This is our product. Eventually, it will reach equilibrium. It doesn't matter that we're just starting with reactants. It will reach equilibrium eventually. Let's take this example here. Now we're starting with 0 reactants and all products. So the reverse reaction will occur, and we'll start to make some reactants, and then eventually we will reach equilibrium. So it doesn't matter what you start with, you will reach equilibrium. So the figure shows that it doesn't matter whether you start with reactants or products, and equilibrium will be reached. And if you notice, the relative amount of change is based on stoichiometry. Look, here we have a 1, a 3, and a 2. And notice that hydrogen is higher than NH3, which is higher than nitrogen. 1, a 3, and a 2. So the equilibrium constant. So consider this general reaction. And we want to write the equilibrium constant in terms of concentration for this reaction. What you're going to do is take your products raised to their coefficients. So D raised to D, E raised to E, divided by your reactants raised to their coefficients. And these brackets here, if you don't remember, mean molarity, which is concentration. But you could also write the equilibrium constant in terms of pressure. So what you would do is take the partial pressure of D raised to its power D, the partial pressure of E raised to its power E, divided by the partial pressure of A raised to little a, the partial pressure of B raised to little b. As long as you have, your gases in a closed system, so the gases are not leaking out. This is your equilibrium constant in terms of pressure. So P is for pressure. So let's do some practice. What are the equilibrium expressions for each of these reactions? So let's look at the first one, and we'll do equilibrium constant for concentration first. So we're going to take our products raised to their coefficients divided by our reactants raised to their coefficients. And now we'll do the pressure one. So we're going to take the partial pressure of oxygen cubed divided by the partial pressure of ozone squared. Now let's do the same thing for this reaction here. And for the pressure, take the partial pressure of NaCl squared divided by the partial pressure of NO squared times the partial pressure of chlorine. So those are your equilibrium expressions. What is the relationship between Kc and Kp? They are not equal, okay? What you have to realize is, if we look at the ideal gas law, we have pressure times volume equals nRT, right? If we divide both sides by the volume, we get P equals moles over volumes times MT, which is just the molarity times RT, right? Where M is your moles over volume or molarity. So you could even write this as concentration times RT if you wanted those brackets. So by plugging this in to the expression for Kp and doing a bunch of algebra, which it actually shows you in your textbooks if you're interested in seeing how it's derived, we get this expression here that the equilibrium constant in terms of pressure is equal to the concentration, equilibrium constant, times RT raised to the delta N. And what is delta N? This is the moles of your gaseous product minus the moles of your gaseous reactant. What does that mean? So say I had this reaction here, and everything is a gas. In my products, I have 1 mole of C and 2 moles of D. So I have 3 moles in my products. Minus, I have 1 of A and 1 of B, 2 moles of my reactants. So that would give me 1. So this would be my delta N. Would be 1 in this case. It depends on your reaction. R is your gas law, and we're going to use the one for ATM, which is 0.0821. And T is temperature in Kelvin. So let's try and do an example. Write the concentration and pressure equilibrium expressions for the following reactions. So let's start with concentration. We have our products. Divided by our reactants. And then for Kp, it would just be partial pressure of N2 times the partial pressure of H2 cubed divided by the partial pressure of NH3 squared. Okay, and from the previous slide, we know that Kp equals Kc times RT raised to the delta N. What is delta N in my case here? So I have 1 mole of N2 and 3 moles of H2. So I have 4 moles total product minus 2 moles reactants. So my delta N is 2. So if Kc is 1.25 and my temperature is 125, what is Kp? So we're trying to solve for Kp. I know Kc is 1.25. T is 125, but that's in Celsius. So to convert it to Kelvin, which is 398 Kelvin. Okay, R is 0.0821, and our delta N that we calculated is 2. So now let's plug everything in. Times our temperature. All of that will be squared. And when you punch all of that into your calculator, you end up with Kp is 1,330. So that is how you convert from Kc to Kp. Notice they are not the same. So let's look at our equilibrium constant. So here we have 4 experiments that we did with different starting initial concentrations of reactants and products. We get our equilibrium concentration, and then we calculate our equilibrium constant. If you notice, the equilibrium constant does not change significantly. And these are all at constant temperature. So as you can see, the ratio of NO2 squared to N2O4 will remain constant at this temperature, no matter what your starting concentrations are. Okay? And you can see here, for experiment 3, you start up here and you end up over here. Experiment 4, you're starting way down here and you're going to end up here at your equilibrium. So your equilibrium constant is called a constant because it is constant. What can the actual value of K tell us? Okay, so what does it mean if K is less than or greater than 1? Okay, if K is significantly greater than 1, and remember K is equal to your products on the top raised to some power over your reactants on the bottom raised to some power. If K is greater than 1, then your products here is larger. So your concentration of products raised to its power is greater than your reactants raised to some power. And that's what this diagram is showing you here. See, your reactants is tiny and your products is huge. So if K is significantly greater than 1, your equilibrium will lie to the right. Now what does it mean it lies to the right? It means that you will have a higher concentration of your products than your reactants. And the reverse is true too. If K is significantly less than 1, that means you will have a higher concentration of reactants than you do of your products. It will lie to the left. What do you think would happen if K is equal to 1? If K is equal to 1, then your concentration of your reactants is equal to your concentration of your products. It doesn't lie anywhere, okay? It lies in the center, I guess you could say. The direction of your chemical equation will affect the value of your K. So the equilibrium constant of a reaction is in the reverse reaction is the reciprocal of the equilibrium constant of the forward reaction. So here we have the forward reaction and we have Kc. Notice the reverse reaction. Notice how these Kc's are related. So K of the reverse reaction will equal 1 over K of the forward. And that's what, if you do 1 over 2.212, you're going to get 4.72. What if your reaction was doubled? Okay, so here is your reaction, N2O4 yields 2NO2, and you multiplied everything by 2. When you double it, if you write your Kc for this, notice your exponents also are doubled. So therefore, your Kc value is doubled. Okay, so in this case, it will be not doubled, but squared. So to find the new equilibrium constant of reaction when the equation has been multiplied by a number, simply raise the original equilibrium constant to that power. Hence, in this example, we're taking Kc squared. Now, what if you have two reactions that when you add them up together, you get the reaction that you're interested in? So you have two consecutive equilibrium reactions occurring that you can add to give a single equation. So can we add these two to get this equation here? Well, let's see. Notice our BRs cancel out, and then we have 2NOBr plus Cl2, 2NO plus 2. So yes, you can. Now, what would be the equilibrium constant for the first reaction? So you have your products. Divided by your reactants. So that's for the first. For the second, you have your products over your reactants. And what would be K for this? You have your products. Divided by your reactants. And they tell us that if we multiply, we'll call this K3, K1 times K2, we should get K3. So let's do that. So K1 times K2 should give us K3. So let's see if that happens. So here's our K1. Times our K2. And let's see what happens. These cancel out, and we end up with NO squared times BrCl squared divided by NOBr squared times chlorine, which is what we need here, right? These are the same. So therefore you could just multiply their values, and that's what they're doing here. So let's summarize what we learned today. At equilibrium, the rate of the forward and the reverse reactions are equal. So you can derive your equilibrium constant. Remember, your products go on top, raised to their coefficients, divided by the reactants raised to their coefficients. We could do this, raising their coefficients, because we're assuming that our steps are elementary. You could also do it for partial pressures. Kp and Kc are related using the ideal gas law, and the relationship you get is as follows, where delta N is your change in moles, moles of product minus moles of reactant in gases. If your K value is significantly greater than 1, then your products are favored. You're going to have a higher concentration of products produced. If Kc is significantly less than 1, then your reactants are favored. The equilibrium constant for the reverse reaction is just equal to 1 over the equilibrium constant for the forward reaction. If you have this reaction and your Kc is this, if you multiply this reaction by 2, you end up just squaring your Kc. And if you have 2 or more reactions that add up to your reaction that you're interested in, then you will multiply their K values. And that is the end of part 1.